this video, I want to talk about Multiversion Concurrency Control, or MVCC. This is something that's super important for how databases manage so many people trying to access the same information at the exact same time. Specifically, this is how MVCC works in Postgres. However, I want to explain this concept in a way that makes sense to people that might not be coming from a super technical background, someone that might not even know what a database is to begin with. So let's start by defining some terms. The first will be a database. So what actually is a database? In its simplest sense, and for the sake of this video, we can think of a database as a one-stop shop for managing all of our data and all of our information. Databases can answer the question of who can access what data and when they get to access it. Specifically, if we're thinking about where our data gets sent and stored and how it's organized, a database has all of that. This is the core of what we're actually interacting with. The second thing I want to define is a transaction. The simplest way to think about a transaction is a method for how we can interact with our database. So specifically, a transaction is actually a sequence of operations that we do on the database. And what that looks like is something like this. We start by issuing a begin command, essentially saying that we're starting a transaction. And then we have any number of actual tasks or operations here. And this can be any number. Literally one operation can be a complete transaction, or even like hundreds or thousands of these. But any of these tasks are sort of anything related to database operations. So this could be selecting and reading information from a table. This could be joining tables or deleting information, updating things, altering things. Anything of that sense is what a transaction actually is. And this is how our users are going to interact with the database. And finally, we have the commit part of the transaction. This indicates that we're finished with the current transaction, that updates that have gone through perfectly with no errors can be reflected to all of the other users of the database. The final thing that I want to define is a snapshot. This isn't too complicated of an idea. We can essentially think of it as a freeze frame of the database, sort of grabbing all the information that we might need from the database at the current time and freezing it at its current moment. So this could grab all of the ongoing transactions, all the transactions that have happened in the past, ones that are soon to come, as well as all of the information from our database itself, the information from the tables, the rows, the columns, all of that sort of stuff. We can store that in our little snapshot. To understand why these terms are useful and how they make sense in the conversation of MVCC, let's look at an example. So here I have a couple of characters which I'm sure are kind of familiar to you. On the left, we have Jerry, and on the right, we have Tom. So in this example, our database is going to be pretty small. It's just a single table with 3 attributes. The first is an ID number, which gives each row its own independent, unique ID to sort of recognize it by. And then the second attribute is a name. The third is an account balance, which in this case reflects how much money Tom and Jerry have in their respective bank accounts. So let's walk through a couple of scenarios and see where problems might arise and how MVCC is actually super important for resolving those issues. So let's say first that Jerry wants to read from his account, essentially determine how much money is in his bank account. This is done, as explained before, through a transaction. So Jerry could issue the begin command, and then Jerry could select information from his account. And if you're not familiar with this, this is SQL syntax. It's not really a big deal to understand it for the sake of this video, but essentially this command should return the actual balance that Jerry has in his account. So in this case, it'll return $1,000. And let's say Tom wants to do the exact same thing. So Tom will issue the begin command, and then Tom will select everything, and then Tom will commit. In this case, we get that Tom has $500 in his account. In this scenario, everything's actually totally fine. We don't have any issues because everyone can kind of read from the database in the same sense. There shouldn't be any issues really caused by this. The real scenario where problems might arise is where one of our two users, in this case Tom or Jerry, tries to write to our database. So let's say Tom chooses to write. And in that case, that could mean that Tom starts a transaction where he wants to actually withdraw money from his account. And for the sake of simplicity, I'll just make that minus 200. And then Tom chooses to commit. So now the actual amount of money that's reflected in Tom's account should be 300. But the way this works in traditional database systems is that in order for Tom to actually change information related to his account, he has to acquire something called an exclusive lock. What that means is that while Tom is trying to withdraw money from his account, no one else can read or write to their account. So what that means in terms of our example is that while Tom is withdrawing $200, Jerry actually can't even check his account balance. Jerry can't check, withdraw, or deposit money into his account. And this seems like a really, really bad situation to be in, especially if you're a bank that has more than 2 cartoon character users. So how do we actually handle this? This is where first snapshots come into play. So if you remember from earlier, our snapshot is really just a screenshot or sort of a freeze frame of the current state of our database. So we can imagine that a snapshot means that both Tom and Jerry both have their own independent sort of freeze frames of the database to operate on. So now let's walk through the same scenario, but just with these snapshots. So let's say Tom wants to write to the database again. He begins his transaction, and then subtracts $200 and then finishes. So now in this case, Tom will start to go through the actions of committing and actually like writing to the database. But at the same time, we're going to say that Jerry wants to read his account balance. So Jerry can read from his snapshot actually. So even when Tom acquires some sort of lock on what's going on here, Jerry can actually just access his account information really quickly and find out that he has $1,000 still, even if Tom is doing something with his account. So this is a really important foundation of how we start to think about MVCC, because if people or users are interacting with just a snapshot of their database, then anyone can read at any time, and these sort of read and write locks don't necessarily conflict with each other. But now we can start to think about what actually happens when Tom commits his transaction, when we actually take away $200 from Tom's account. We don't want Jerry's information to be incorrect here. And for the sake of simplicity, again, we're assuming that there aren't these sort of like row level locks that say that Jerry can only access this information here and only Tom can access this information. To understand MVCC, we're just going to say that everyone can sort of access any of these rows in the table. But as soon as Tom withdraws $200, we don't want Jerry to have 500 still here in this account balance, or Tom really. So how do we actually get the update to be reflected? That's where multi-version concurrency control actually comes into play. So this is what the table looked like originally. So now let's say that after Tom's write operation, where he subtracts $200, this is what would actually happen to our table when we modify it. So we would add a new row, actually. Sorry, that's a bad one. We can add a new row here. And in this case, we'll have the same sort of ID number, so you can just copy that over. The same name because it's Tom making the change. But now the reflected value is $300 because Tom just issued a transaction to subtract $200. But the key extra information that we have here is that these rows actually have version numbers attached to them. So now our database knows that this is the original value, the original row that we had in our database, and this is the follow-up version. So now we know that anyone who's accessing our database should be looking at this newer, updated second version. So now Jerry from earlier, who actually is issuing a read command and just wants to, again, begin as transaction and then select everything from the database and then finish, just a simple interaction. Now, when they're retrieving information from the database, they're going to specifically get the highest version number that exists in the database, which means they're not going to be referencing this old version of Tom's account balance. And instead, they're going to see that not only do they have $1,000 still, but Tom now withdrew $200 and has $300 left in his account. So this is in essence how we have multi-version concurrency control. Multi-version sort of meaning that we have multiple versions of these rows or tuples in our database. And those indicate versions that exist because of different transactions, different updates, different changes to the tables and information in our database. But you might notice a problem can arise with this sort of multi-version concurrency control. If we have a lot of updates, we have a lot of users, we could very easily see something called bloat happen in our table, where we end up with several versions of these sort of tuples. And this becomes a real problem when you're thinking about large-scale database systems, because we don't actually know how to manage this many things in the database. And so this is a separate issue, actually. There are solutions for this, and there's actually a process in Postgres called the vacuum, which does a lot of work to resolve removing these dead tuples, but that I'll save for another video probably. But overall, this has sort of been a high-level overview of how multi-version concurrency control actually works. This concept is super important for making sure that people can access information super quick, making sure it's readily available despite other transactions going on and despite locks and restrictions that other transactions are trying to impose on the database.